In this lesson, we're going to look at the types of elements that form an ionic bond, explain how an ionic bond is formed, and then learn how to predict the formula of an ionic compound now that we know whether an element is likely to form a cation or an anion and what its most probable charge is. Ionic compounds form from cations and anions. Cations are typically formed from metals, and they lose electrons to form those cations. Anions tend to form from nonmetals, and they gain electrons to become an anion. Our metals are found on the left side of the periodic table. Nonmetals are found on the right, with the exception of hydrogen. We will not look at any metalloids forming ionic compounds. Ionic compounds form from the transfer of an electron from one species to another. In this case, we're looking at the example of sodium and fluorine. Sodium has one valence electron, and it wants to get rid of that electron in order to form the +1 cation and to have 8 electrons in its outermost shell. Fluorine has 7 valence electrons. It wants to gain 1 electron in order to have 8 electrons in its outermost shell. So sodium gives up its 1 electron from its valence into fluorine's valence shell. And now both sodium and fluorine will have 8 valence electrons. Sodium will have formed a cation with a +1 charge. Fluorine will form an anion with a -1 charge. And because of those opposite charges, they will then be attracted to one another and form what we call an ionic bond. Now we want to look at how we can determine the ionic formulas from a pair of atoms. Let's start with our example of sodium and fluorine. When we look at sodium, we know it's a metal. It has 1 valence electron, so when it forms an ion, it will form a +1 charge. Fluorine is a nonmetal with 7 valence electrons, and when it forms an ion, it will form an ion with a -1 charge. Much like in our chemical formulas where we omitted the number 1 and just assumed it was implied, we do the same thing with our charges. For example, when we write the plus sign, what we really mean is +1. For a minus sign, it just means -1. So the 1 is usually implied and not explicitly written. We know that an ionic compound needs to be neutral. The number of electrons lost to form cations must be equal to the number of electrons gained to form the anions. And one way we can figure out what the formula is going to be is something called the crisscross method. So if we look at sodium with its +1 charge and fluorine with its -1 charge, we can move the 1 to the subscript of fluorine. We can move the 1 from fluorine to the subscript of sodium, and we get Na1F1. Notice we have 1 of each. We have omitted the signs because we're just worried about how many sodiums and how many fluorines. We're not worried about the plus and minus charge when we're actually showing the formula. Because 1s are implied in our chemical formulas, we can rewrite this simply as NaF. And because our compounds are going to be overall neutral, we know that we have a +1 from the sodium plus a -1 from the fluorine, and those add up to an overall charge of 0. Because ionic compounds have a neutral charge. Let's look at another example with potassium and chlorine. So potassium, like sodium, has a 1 valence electron, and so it will form a +1 charge. Chlorine, like fluorine, has 7 valence electrons and will form a -1 charge as an ion. And when we crisscross down, we put the 1 from the potassium on the chlorine subscript. The 1 from the chlorine becomes the subscript for the potassium, and we get KCl, and we can rewrite that without the 1s because we know that the 1s are implied. Just like before, we can check to see that this is correct because we have +1 from the potassium plus a -1 from the chlorine, and we see that that equals 0. Now let's look at an example where we don't have both plus and -1 charges. When we look at calcium, we see that it's in the second column of the periodic table. It has 2 valence electrons and will form an ion with a +2 charge. We generally write the number before the sign when we're writing the charge on ions. For bromine, it's like fluorine and chlorine. It's in the second to last column, has 7 valence electrons, and will form an anion with a -1 charge. We can still do the crisscross method. The 2 becomes the subscript for the bromine, the 1 becomes the subscript for the calcium, and we write Ca1Br2. We can remove the 1 because we know that the 1 is always implied when no subscript is given, but we must keep the 2 so that we know for every 1 calcium we need 2 bromine anions. When we look at our charges, we see that calcium has a +2 charge, plus 2 of the -1 charges for bromine, and when we add them up, we get an overall sum of 0, which is what we want since we know that ionic compounds are neutral. Let's look at aluminum and sulfur. Aluminum has 3 valence electrons and will form a 3+ charge. Sulfur is like oxygen and needs to gain 2 electrons to look like the nearest noble gas, so it will have a -2 charge. We crisscross down and we get Al2S3. We cannot simplify this any further because that is the lowest whole number ratio between the aluminum and sulfur that will give us a neutral compound. We can check that it is neutral by saying 2 times +3 for the 2 aluminums, plus 3 times -2 for the sulfurs, and when we add that up, we get that it sums to 0. Looking at magnesium and oxygen, we see a new scenario. We know magnesium forms an ion with a 2+ charge. Oxygen forms an ion with a 2- charge, and when we crisscross down, we end up with Mg2O2. For ionic compounds only, we can reduce this to the smallest whole number ratio. Remember when we looked at ionic compounds, we see they exist as a continuous network where we're only worried about the ratio of cations to anions. So for ionic compounds, we can reduce the subscripts down to the lowest common whole numbers. In this case, we could rewrite it as MgO. When we have the +2 from the magnesium plus the -2 from the oxygen, we get that it sums to 0. Note that on molecular compounds, we cannot change the subscripts to any other numbers because they exist as discrete molecules. For ionic compounds, our metals and nonmetals, we can reduce those subscripts to the lowest whole number ratio between those elements. Now let's look at an example involving a transition metal. Here we have Fe3+ and oxygen. For transition metals, we cannot predict their charges based on what we see in the periodic table, and so additional information has to be given so that you know the charge for transition metals. Here we're going to have our Fe3+, our oxygen 2-. We're going to still do our crisscross down, and we end up with Fe2O3. We can check that our overall charge is neutral by taking 2 times +3 plus 3 times -2 and getting a sum of 0.